is Ogechi. All man supposed know.
Hi, how are you doing? My name is Ogechi Igboanugo. I'm a CCIE and JNCIE for service provider and enterprise environment. Okay, last video we talked about types of routing protocols, right? I talked about dynamic routing protocols, static routing protocols. I talked about the types of dynamic routing protocols, the two major hierarchies, IGPs and EGPs. And I even went further to break down the types of IGPs that exist today. I talked about distance vector routing protocols, link state routing protocols, and the hybrid routing protocols. And I talked about EGP, the only EGP that exists today, and that is BGP. Okay, today we'll be talking about the differences between all these types of routing protocols, the differences between these dynamic routing protocols. So stay tuned and enjoy the show. Oh, and by the way, in the next video, I'll be showing you guys live on the CLI, on the command line interface of a Juniper and a Cisco router. I'll show you all these protocols live so you can see how they interact with each other. Okay, stay tuned, enjoy the show. My name is Ogechi. So RIP version 1 was a classful routing protocol. So by classful, it didn't really care about subnet masking. In fact, it did not care about subnet mask information. It could not do variably length subnet masking. So it only cared about major networks, right? So it was classful in nature. There was no subnet information. If you had a subnet of 12.12.12.0/24 and then using RIP version 1, what happens is that it's just gonna summarize it to 12.0.0.0/8. This is how RIP understands this. But the other routing protocols, right, that are classless, they would keep the summary, the subnet like this. But RIP version 1, it only understands classful major networks. So it will see the 12.12.12.0 as 12.0.0.0/8 because its major network lies between that range as a class A network. So class A lies between 1.0.0.0 to 127.0.0, 127.255.255.255. So 12.0.0 falls within the class A network, right? And that is why RIP would see it as a major network of 12.0.0.0, RIP version 1 only. The others understand subnet variable length subnet masking. RIP version 2 was classless. Now I know it sounds kind of weird, right? Classless and classful. And classless is actually better, or an enhancement to classful. So classless is actually better than classful, right? Sounds weird, right? So yeah, RIP version 2 was a classless routing protocol. And by classless, it allowed variably length subnet masking. It encouraged subnet mask information, right? So it allows for more control for the administrator, right? Because you can now subnet networks, into smaller bits and advertise that information. OSPF also was classless. ISIS is classless also. EIGRP classless, and BGP is also classless. RIP version 1 was very chatty. It wasn't really like efficient, right? So RIP version 1 sends updates of the entire routing table every 30 seconds. Now let me describe this communication behavior. So imagine Gary is talking with Peter right here, right? And Gary has told Peter, "Hey, my name is Gary. My name is Gary." Imagine Gary is saying every 30 seconds, "Hey Peter, my name is Gary. My name is Gary." You see, it's kind of weird, right? Imagine having a communication with somebody and the person is repeating the same thing that you already know about every 30 seconds. And that was RIP version 1. So that wasn't really efficient, right? So they came about, auto enhancement to make communication better. So yeah, RIP version 1 every 30 seconds. RIP version 2 also did similar thing. It sends updates every 30 seconds too, not too efficient. OSPF sends updates when there's a topology change. So when you need a new information, that's when it tells you, oh, there's been a new change to my information. This is a new change, basically. So going back to our analogy, if Gary tells Peter, "Hey, my name is Gary," And Peter says, oh, okay, your name is Gary. Gary, how you doing? And Gary says, but my last name is also Checker. So my full name is Gary Checker. Peter will be like, oh, okay. Okay, welcome, Gary Checker. So now Peter has understood now that Gary first told him his name was Gary. And later, Gary says, hey, my last name is called Checker. So Gary is updating Peter every time there's an update. Peter did not know about his last name before, but Gary updated Peter later on, right? And now through the conversation, Gary might tell Peter other information. So basically, OSPF and the other routing protocols, they send out updates only when there's a topology change. That's more efficient, right? Okay, cool. Now, the way routing protocols know how to reach a destination is through like a metric system, right? There's some algorithm that enables them to know, okay, I have these routes. This is the best way to reach this route, right? So there's some algorithm that determines the distance to a route. For example, if you're traveling from here, Dallas to Florida, right? I could go online and look for a flight. I'll look for the cheapest flight, or I'll look for an airline. I'll check out how far it is. Or if I want to drive to Florida, I'll check out, how far is it going to take me to drive to Florida, right? So basically, the distance to a destination, checking all the metrics, right? Like the flight, the price of my flight, or the price of manually driving to Florida. I'm going to consider all those factors before I determine, okay, this is my best route to Florida. That's what routers do. They determine the best way, the best metric to reach a destination. So the metric system of RIP version 1 and RIP version 2 is called hop count. As easy as hop count. Now, and that's why they're called distance vector routing protocol, because they consider distance as a major factor. Bring back my whiteboard. For RIP, say you have these routers, right? RIP considers distance to reach a route, basically. So for example, if this route is 10.1.1.1, right? And RIP, this guy is 10.2.2.2. This router 1, this is router 3. This is router 2 over here. Now router 1 wants to get to router 3. So what RIP will do is it looks for its nearest path to get to router 3. So if it takes this path, this is one hop, right? One hop to get to router 3. It's one destination, one jump to get to router 3. And if router 1 took the other path, this is one hop to get to router 2 and another hop to get to router 3. So making this 2 hops in total, right? While this is 1 hop in total. RIP will choose this path because it's 1 hop, basically. So that's how RIP evaluates routes. It uses a hop system. Now, the problem with RIP, right, was that, yes, the hop system makes sense, right? Because, yes, router 1 will go directly to router 3 to reach this network, versus going 2 hops away through router 2 to reach this network, right? But what if the link between router 1 and router 3, right, was 5 meg in bandwidth? And what if the link between router 1 and router 2 was 1 gigabyte, right? And the link between router 2 and router 3 was maybe 10 gig. So you see, it's actually inefficient for router 1 to take the 5 meg path, because if you're considering bandwidth, imagine you're trying to do a large file transfer, right? You're taking the least path with the worst bandwidth because it's just 1 hop away. So RIP will choose this path, even though it's just 5 meg of available bandwidth, where it would have considered using the larger bandwidth path, but because it's RIP, it doesn't factor bandwidth into consideration. So that was a flaw, a major flaw of RIP. Now, OSPF considers the bandwidth. It takes that into consideration. So for OSPF, the cost, also ISS, the cost is calculated somewhat as the inverse of the bandwidth. So the greater the bandwidth, the lower the cost. And lower means better. So for the 1 gig and 100 gig path, I'm just using make-believe cost right now because you can manipulate cost. Let's say I manually make this cost between this link 10, a cost of 10, and I make this one a cost of 2. But for a 5 meg link, OSPF or ISS would make this maybe worse. These are just made up values, right? It's not the exact values on the routers. So let's say I make this link 100. So when OSPF looks at this, it's gonna take this path because it's gonna calculate what is the total cost for me to reach 3.3.3.3 from router 1. So if I add the cost to get to router 2 is 10. Then the cost from router 2 to get to 3 is 2. 10 plus 2. So my total cost is going to be 12. So router 1 has a total cost of 12 if it takes this path. And that's what OSPF is taking into consideration. Also, ISIS. But the cost, if I was taking this other path, the cost is 100. So OSPF sees that the path with the greater bandwidth, even though it's 2 hops, has a better cost. And it takes that path. And that's how efficient ISIS and OSPF is. It considers bandwidth too. EIGRP also has a bandwidth consideration. You can set for EIGRP by default, you can set the minimum bandwidth and the delay. It takes that into consideration, and it takes the right path also. So that's this was a major drawback of RIP, right? Because RIP was only routing based on rumor, routing based on hop count as well, even though it was inefficient. It exchanges updates periodically every 30 seconds. It's sending chatty updates every minute, right? Every 30 seconds, and it's commonly called routing by rumor. So basically, it just does some weird stuff. Now going back to our analogy, right? Say Gary is telling Peter about some information. Gary heard that information from Phil. Phil heard that information from somebody else. So you see, there's a chain of rumor, right? And you know, when rumor is heard from one person to the other, when it gets to the last person, that rumor is not really like valid anymore, right? You know, each person at each hop can add one information or the other and stuff like that. So it's not really efficient, right? You know how rumors go, right? So basically, that's how RIP worked. It's routing by rumor, and that was not really efficient. Also, RIP had a limit to its hop count. It's a limit to its metric system. Its metric system was hop count, just like I mentioned here, right? Metric system is being hop count, but it had a limit. It was like from 0 to 16, of which 16 means like it's a dead route, you know. But imagine you were putting RIP on the internet. Internet is like a lot of hops away. You have routers multiple hops away, right? So having 16 as your limit, or 15 valid routes, 15 hop as a limit, your valid limit, it doesn't sound scalable, right? So RIP definitely cannot be deployed on the internet. So it's not efficient in any way, right? It's still a routing protocol and it still works, basically. So yeah, that's that about RIP. Now for OSPF uses a cost system to evaluate its distance towards routes. Now cost is like some algorithm, some metric calculation, right? Now the larger the bandwidth, the better the cost, right? The smaller the bandwidth, the worse the cost, right? So basically, the smaller costs, the better. The smaller the cost, the better, basically. So OSPF uses a cost system that also considers bandwidth as a factor. ISS also uses a similar cost algorithm too that considers bandwidth as well. Now EIGRP has a bunch of factors. It has factors like minimum bandwidth, the delay across the link, load, MTU, and reliability of the link. It has a lot of factors, but EIGRP was still distance vector in nature because it considered distance, right, to reach something, right? But it also considered link attributes too and delay. So it was like a hybrid, right? So it was kind of like a hybrid because it uses the best of both worlds, the distance vector information and also link state information. BGP is more It's more advanced, right? Like its algorithm system, it uses the BGP best path selection algorithm. Best path attributes. Attributes like weight, local preference, ASPath, MED, just to mention a few. So BGP was more intense, but it's more efficient because it gives you more granular control over your route information. And that's why it's used on the internet, because it's very granular. Going back to our differences, RIP version 1 is a distance vector routing protocol, right? Version 2 is also a distance vector routing protocol. OSPF and ISIS are both link state routing protocols. EIGRP is a hybrid, right? It's, according to Cisco, it's an enhanced distance vector routing protocol, but it's a hybrid, right? Because it has some link state attributes too. BGP is an EGP. So for RIP, it uses Bellman Ford algorithm. RIP version 1 and RIP version 2 use the Bellman Ford algorithm. OSPF used the Dijkstra algorithm. ISIS, being a link state protocol, also uses the Dijkstra algorithm. EIGRP uses the dual algorithm, diffusion update algorithm. That's what dual means. Whereas BGP uses the BGP best path selection algorithm. Now, all these protocols, RIP is not so scalable. RIP version 2 was an enhancement of RIP version 1, right? So it was a bit scalable, but it's not really that scalable. OSPF is very scalable, especially for within an AS IGPs, right? It's very scalable. It's very hierarchical in nature. ISIS is also scalable and hierarchical. It just depends on your implementation, how you manage your topology. EIGRP is also very scalable and pretty fast as well. BGP is very scalable. Say I called it more scalable, but that's in my own interpretation. I really love BGP. I love BGP. Okay, cool. Now, in a firewall point of view, normally as a network administrator or a network architect or engineer, it's always good to understand like implications, right, of firewalls. So when you're trying to put the firewall rule or whatever, ensure to allow these protocols through, right? So basically, RIP operates as a UDP protocol under port 520. So that's the port for RIP, UDP port 520. If this is blocked, your RIP communication between two routers would be stopped. So always ensure that UDP is allowed between your routers, right, on that port 520, because that is the port that RIP is listening to. For OSPF has its own IP protocol, and it's IP protocol 89. ISIS is not an IP. It was not originally an IP protocol. It was a connectionless network service. ISIS was created by ISO back in the day, and it was actually operating under the OSI model standard. There's an IP version, right? The one there's a version that is that can do IP, right? And that's the integrated ISIS. Then EIGRP has an IP protocol 88. Now for BGP operates as TCP, under TCP, right? And it's port 179. Cool. Now for authentication, RIP version 1, this is RIP version 1, has no authentication. RIP version 2 allows for authentication. The rest of the dynamic protocols allow authentication as well. Okay, now just looked up OSPF on Wikipedia. It says open shortest path first, and let's just see what it says. It says let's look for its origin history, right? That's very important information. Let's see when it was created. It says as a link state routing protocol, it was based on the link state algorithm developed for the ARPANET in 1980 and the ISS routing protocol. OSPF was first standardized in 1989. Wow, that's a long time ago. And that was OSPF version 1. So that's the origin of OSPF. It has long since then gone through a lot of enhancements, right? We even have OSPF version 3 that carries IPv6 and IPv4 addresses right now. So OSPF has gone a long way, and it's very popular. Now for ISIS, intermediate system to intermediate system, ISIS, let's look for its history. ISIS was developed by a team of people working at Digital Equipment Corporation as part of DECnet. It was standardized by the ISO in 1992. You can see that. Yep, that was a long time ago. ISIS is very extensible. It's getting popular again. Really, a lot of ISPs use ISIS in their core. ISIS is very extensible. It has TLVs, type length values, that allows it to, instead of building a new routing protocol, right? So what we've done with technology is we reuse like the existing protocols like ISIS. Because of its TLVs, now a lot of cool stuff can be done with ISIS. ISIS can carry IPv6 information. It was used as a core in fabric path technology. It even carries segment routing information too, right? So ISIS is very extensible, and I think it's going to go a long way as a good link state routing protocol. Let's go to EIGRP. EIGRP, let's see what it has to do. So for EIGRP, look up at Wikipedia. It says Enhanced Interior Gateway Routing Protocol, EIGRP. Is an advanced distance vector routing protocol. See what it says? And that's what Cisco says too, right? But we call it hybrid. So it's history. Let's see when it was created. When was it created? It doesn't really say. It's now open standard, right? It was converted to open standard in 2013. Originally, it was made by Cisco, right? EIGRP replaced Interior Gateway Routing Protocol, IGRP, in 1993. One of the major reasons for this was the change to classless addressing. IGRP could not support classless addressing. You see? So that's another good information. Let's go to BGP to see when it was first created, to see its history. History of BGP, right? That would be cool to see. As for BGP, Wikipedia says BGP's border gateway protocol. It's a standardized exterior gateway protocol, just like I said. Its history. Border gateway protocol was first described in 1989 and has been in use on the internet since 1994. IPv6 BGP was first defined in 1995. Yeah. So yeah, that's the history of BGP. This is awesome. This is great information.